Last time you did Gaussian elimination by writing row operations in the margin. Subtract 3 times row 1 from row 2, subtract 2 times row 2 from row 3, a sequence of instructions. Every one of those instructions is secretly a matrix. The entire elimination process is one matrix times A. Here's our destination, E sub 3,2 times E sub 2,1 times A equals U. Let's build this from scratch. To see why elimination is matrix multiplication, we need two ways to think about a matrix times a vector. Let's start with the column view. Take A equals the 3 by 3 matrix with rows 1, 2, 1, 3, 8, 1, and 0, 4, 1. We multiply A by the vector 3, 4, 5 transpose. Using the column picture, this product equals 3 times column 1 of A plus 4 times column 2 plus 5 times column 3. That gives us 3 times the column vector 1, 3, 0 plus 4 times the column vector 2, 8, 4 plus 5 times the column vector 1, 1, 1. Computing each scaled column, we get 3, 9, 0 plus 8, 32, 16 plus 5, 5, 5. Adding these together component by component, we get 16, 46, 21. This illustrates the key principle. A matrix times a column vector is a linear combination of the columns of that matrix. Now flip everything. Put a row vector on the left side of the matrix. Take the row vector 1, 2, 7 and multiply it times A. This product equals 1 times row 1 of A plus 2 times row 2 of A plus 7 times row 3 of A. That gives us 1 times 1, 2, 1 plus 2 times 3, 8, 1 plus 7 times 0, 4, 1. Scaling each row, we get 1, 2, 1 plus 6, 16, 2 plus 0, 28, 7. Adding these together, the result is 7, 46, 10. Here is the key principle. A row vector times a matrix is a linear combination of the matrix rows. This is the side that matters for elimination. Row operations come from multiplying on the left. Here's a side-by-side summary of the two viewpoints. On the left, we have the column view. The operation is a matrix times a column vector. The result is a column vector. The interpretation is that we get a linear combination of the columns of A. This view is relevant for understanding the column space, and it corresponds to right multiplying. On the right, we have the row view. The operation is a row vector times a matrix. The result is a row vector. The interpretation is that we get a linear combination of the rows of A. This view is relevant for elimination and row operations, and it corresponds to left multiplying. For elimination, the row view is what matters because left multiplying a matrix performs row operations on it. This is the key insight that will drive everything we do with elimination matrices. Left multiplying performs row operations. We need a matrix that does one specific step. Subtract 3 times row 1 from row 2. Let's build it step by step. Start with the 3 by 3 identity matrix. Its diagonal entries are all 1s and everything else is 0. Now look at row 2 of the identity. It's 0, 1, 0. When this row left multiplies A, it selects row 2 of A unchanged, but we don't want row 2 unchanged. We want row 2 minus 3 times row 1. So here's the key move. We replace the 0 in position 2, 1 with negative 3. Row 2 of our matrix becomes negative 3, 1, 0. Notice the multiplier was 3, so we place negative 3. It's always negative. That's because we're subtracting. And this gives us E₂₁, an elimination matrix, a matrix that performs a single elimination step. And the subscript is a helpful mnemonic. E₂₁ means the target is row 2. The pivot comes from row 1, and the entry sits in position row 2, column 1. Meanwhile, rows 1 and 3 of the identity stay completely untouched, so rows 1 and 3 of A pass through unchanged. Let's verify that E₂₁ actually works. Take A equals the 3 by 3 matrix with rows 1, 2, 1, 3, 8, 1, 0, 4, 1. we'll compute the 2-3 entry of E₂₁ times A using the dot product rule. We dot row 2 of E₂₁ with column 3 of A. Row 2 of E₂₁ is -3, 1, 0. Column 3 of A is 1, 1, 1 transpose. Now we multiply term by term. -3 times 1 equals -3. Then 1 times 1 equals 1. Then 0 times 1 equals 0. Accumulating these, we get -3 plus 1 plus 0, which equals -2. Let's check this by hand. The third entry of row 2 in A is 1, and the third entry of row 1 in A is also 1. Row 2 minus 3 times row 1 gives 1 minus 3 times 1, which is 1 minus 3, equal to -2. It matches, so the elimination matrix E₂₁ does exactly what it's supposed to do. One step captured. Now the second, subtract 2 times row 2 from row 3. Same recipe, start from the identity matrix and place -2 in position 3, 2. That gives us E₃₂ equals the matrix 1, 0, 0 in the first row, 0, 1, 0 in the second row, 0, -2, 1 in the third row. Now let's apply it. First, E₂₁ times A gives us the intermediate matrix 1, 2, 1 in the first row, 0, 2, -2 in the second row, 0, 4, 1 in the third row. Row 1 is unchanged, row 2 has been updated, and row 3 is still untouched. Then E₃, 2 times that intermediate matrix gives us 1, 2, 1 in the first row, 0, 2, -2 in the second row, 0, 0, 5 in the third row. That is U, an upper triangular matrix, meaning all entries below the main diagonal are 0. Every elimination step was captured as a matrix multiplication. We have E₃₂ times E₂₁ times A equals U. Now, matrix multiplication is associative, which means you can regroup the parentheses without changing the result. So E₃₂ times the quantity, E₂₁ times A equals the quantity, E₃₂ times E₂₁ all times A. Both groupings give you U. This means E₃₂ times E₂₁ is a single matrix that performs all of the elimination at once. Let's compute that product. E₃₂ times E₂₁ equals the matrix 1, 0, 0, -3, 1, 0, 6, -2, 1. Notice the 6 in position 3, 1. Now let's see what happens if we swap the order. E₂₁ times E₃₂ equals the matrix 1, 0, 0, -3, 1, 0, 0, -2, 1. Look at position 3, 1. It has 0, not 6. These two matrices are different. This demonstrates a crucial fact. Matrix multiplication is not commutative. You cannot swap the order of multiplication. So to summarize, associative, yes, you can regroup freely. Commutative, no, you must never reorder. Step back and look at what we've built. Elimination, something that felt like a recipe of instructions, is actually pure matrix algebra. Every single step is a matrix. The whole process is a product of matrices. E₂₁ subtracts 3 times row 1 from row 2. E₃₂ subtracts 2 times row 2 from row 3. A is the original matrix and U is upper triangular. Putting it all together, E₃₂ times E₂₁ times A equals U. And because matrix multiplication is associative, E₃₂ times E₂₁ collapses into a single elimination matrix. This is the big picture. Elimination is just multiplying by matrices on the left. Next time, we ask the reverse question. If these E matrices take A to U, what matrix takes U back to A? That's the inverse. And undoing elimination turns out to be even cleaner than doing it.